We're never going to stop exploring the unknown in air and space. We have ignition and we have liftoff. The response was normal. The launch of NASA's Voyager probes marked the inception of an extraordinary interstellar odyssey, showcasing our ability to explore not only Earth but also the vast reaches of our solar system and beyond. Even after 45 years in space, these exceptional spacecraft persist in providing scientists with continuously evolving insights into the mysteries of the cosmos. Despite possessing a memory capacity 3 million times smaller than a typical smartphone and operating at a speed 38,000 times slower than a 5G internet connection, these pioneering probes remain at the forefront of space exploration, defying technological limitations. In a surprising turn of events, the Voyager probes have now made an astonishing discovery. The question arises, what are they doing at this very moment? What awaits the voyage of these spacecraft as they navigate through the uncharted realms of the cosmos? Let's embark on a journey to uncover the latest revelations and unravel the mysteries that lie ahead for these venerable emissaries of human curiosity. On September 5, 1977, a remarkable journey began from Cape Canaveral, Florida, as Voyager 1 was launched into space riding the Titan IIE rocket. Just 15 days later, on August 20, 1977, Voyager 2 followed suit, embarking on a twin odyssey into the cosmos. Their primary mission aimed to explore the gas giants of our solar system, Jupiter and Saturn, along with the moons orbiting them. However, these intrepid explorers surpassed their initial objectives, venturing to the farthest reaches of our celestial neighborhood. Voyager 1 and Voyager 2 have set numerous records during their epic journey, traveling farther from Earth than any other human-made objects and marking their entry into interstellar space. A historic achievement as the first human-created objects to do so, as pioneering interstellar probes position themselves more than 12 billion miles from Earth. They continue to astonish physicists with their findings. A recent and unexpected discovery, which we will delve into later, adds to the intrigue of their journey. The accomplishments of the Voyager twin probes have been nothing short of spectacular. Their early observations over 40 years ago of Jupiter and Saturn's moons defied previous assumptions, revealing geological activity on moons thought to be as inactive as our own moon. Voyager 2, in particular, achieved significant milestones during its journey, becoming the first spacecraft to pass by Uranus in 1986 and conducting a flyby of Neptune just 3 years later, a path no other spacecraft has ventured. As the spacecraft continue their remarkable voyage, NASA has implemented measures to extend their operational lifespans. Over the past 3 years, non-essential components and heaters have been deactivated to conserve energy, allowing them to operate until an estimated mission end date of 2030. For the dedicated scientists and engineers who have been part of this extraordinary journey since its inception, the culmination of the Voyager missions is bittersweet. Their dedication has seen the project through far beyond initial expectations. The data returned by the Voyagers has provided valuable insights, fueled countless scientific discoveries, and inspired generations of researchers and space enthusiasts. Meticulously designed as stable platforms, with a rotation rate more than 15 times slower than the hour hand of a clock, Voyager 1 and Voyager 2 were not just ordinary spacecraft. They were marvels of engineering that captured the imaginations of all who followed their epic exploration. These images unveiled towering volcanic plumes and a surface marked by the ejection of volcanic material. Pele, one of Io's prominent volcanoes, erupted 30 times higher than Mount Everest, covering an area nearly the size of France. The Voyager spacecraft captured over 33,000 images of Jupiter and its moons, showcasing the planet's beauty and the incredible diversity of moonscapes in the Jovian system. Before the recent mind-boggling discovery, the twin Voyagers had been making breathtaking findings since their launch. One of the most surprising revelations was the existence of Jupiter's rings. Though faint, these rings were a revelation, adding to the allure of the gas giant. Voyager 2 also uncovered that Europa, one of Jupiter's 53 named moons, possessed an icy shell believed to be over 60 miles thick. These findings challenged previous assumptions about the nature of these distant celestial bodies and sparked further investigations into the potential habitability of icy moons. As the Voyagers bid farewell to Jupiter, they received a gravity assist, providing them with a vital boost propelling them toward Saturn. Without this assistance, they wouldn't have escaped the sun's gravitational pull to venture further into space. Voyager 1 and Voyager 2 then took different paths. Voyager 1's journey led it close to Saturn's moon Titan, shrouded in an orange hazy atmosphere. This moon's mysteries intrigued scientists, prompting further studies into its complex chemistry. Voyager 1 then turned northward, departing from the planets and beginning its journey beyond our solar system. Voyager 2, on the other hand, embarked on a series of adventures that took it to the outermost planets. In 1986, it made a historic flyby of Uranus, discovering 10 previously unknown moons. 3 years later, Voyager 2 reached Neptune, unveiling the remarkable features of this distant ice giant, including wind speeds of up to 1,000 miles per hour, the fastest ever recorded on a planet in our solar system. During its encounter with Neptune, Voyager 2 provided unprecedented insights into this distant world. Triton, Neptune's largest moon, was found to be one of the coldest places in the solar system, with surface temperatures plummeting to -391 degrees Fahrenheit. Triton also exhibited unique features, including ice volcanoes ejecting nitrogen gas and icy particles. These discoveries expanded our understanding of the variety and complexity of celestial bodies in our solar system, even in the outermost regions. A key figure in extending the mission beyond their initial goals was the renowned astronomer Carl Sagan, a member of the Voyager mission's imaging team. He passionately advocated for capturing one last set of images before turning off the cameras on both spacecraft. Sagan's persistence paid off on Valentine's Day in 1990, when Voyager 1 turned its camera back toward the inner solar system and captured a series of 60 images. The most iconic, known as the pale blue, remains an unforgettable symbol of our place in the cosmos, taken from a distance of 38 billion miles. The Voyager mission is a remarkable tale of durability and longevity that reads like a space-aged superhero comic. Even after 40 years, they're still out there, continuing to send us valuable data from the furthest reaches of our cosmic neighborhood. Now, let's dive into the fascinating realm of the Voyager probe's archaic 8-track tape system. Yes, you heard it right. 8-track tapes were all the rage in the 70s, and remarkably, the Voyager probes still rely on them. It's a testament to the ingenuity of the mission's designers that these dependable tapes have endured the test of time. But why 8-track tapes, you may wonder? In the early days of space exploration, digital storage as we know it today was still in its infancy. They needed a reliable and durable data storage system, and those 8-track tapes fit the bill. They're like the indestructible workhorses of the cosmic age. What makes it even more incredible is that the data on these tapes isn't your typical tunes. It's precious scientific data about the outer planets, moons, and interstellar space. Yes, these tapes hold the key to unraveling some of the most profound mysteries of the universe. Now let's discuss the strategies that ensured the success of the Voyager missions. One crucial technique employed was gravity assist maneuvers, and their role in these legendary interstellar missions was nothing short of brilliant. Picture two intrepid spacecraft, Voyager 1 and Voyager 2, embarking on their audacious quest to explore the outer reaches of our solar system. To reach these distant destinations and gather invaluable data, they needed a boost beyond their own propulsion systems. This is where gravity assists come into play, a bit like cosmic choreography. Instead of solely relying on their engines, these spacecraft performed a celestial dance with some heavyweight planets in our solar system, using the immense gravitational pull of these giants to slingshot themselves on their way. This clever maneuver allowed them to conserve precious fuel and gain the velocity needed to visit multiple destinations on their grand tour. Let's break it down. Gravity assist, also known as a gravitational slingshot, involves transferring some of a planet's momentum to the spacecraft as it passes by. Imagine Voyager 1 approaching Jupiter, a massive gas giant with a gravitational pull to match. With precision only achievable by the brightest minds at NASA's Jet Propulsion Laboratory, Voyager 1 swung by Jupiter at just the right angle and speed. Jupiter's gravity tugged at the spacecraft, accelerating it to a higher velocity, a cosmic boost giving Voyager 1 the oomph it needed. But here's the art in this maneuver. If Voyager 1 had approached Jupiter at the wrong angle or speed, the slingshot could have been a cosmic catastrophe, sending the spacecraft off course. The precision required is mind-boggling, yet the scientists and engineers behind this cosmic ballet got it right. Not just once, but multiple times. These gravity assists propelled Voyager 1 and Voyager 2 on a breathtaking journey through the solar system. Voyager 2, for instance, utilized gravity assists from Jupiter and Saturn to travel to Uranus and Neptune. These celestial dancers were pivotal in making the Grand Tour possible, and the Voyager missions wouldn't have been the same without these slingshots. Voyager 1 ventured into interstellar space, and Voyager 2 swiftly followed suit, all thanks to the precision of these gravity assists. The concept behind gravity assists is simple, but the execution is breathtakingly complex. Voyager 2's Grand Tour demanded an incredible level of precision, and missing any of these slingshots could have spelled mission failure. The dedicated individuals behind these missions were determined and relentless in their pursuit of knowledge. Although the Voyager missions relied on gravity assist maneuvers to navigate the cosmos, these missions would have remained celestial daydreams without another critical component: the Deep Space Network, DSN. Think of it as the interstellar telephone line that kept us connected with our intrepid Voyager probes as they journeyed into the great unknown. So what exactly is the Deep Space Network? It's not as flashy as a spacecraft, but it's just as vital. The DSN is a network of massive radio antennas strategically located in various corners of the world, including California, Spain, and Australia. Ranging from 26 meters to a whopping 70 meters in diameter, these gargantuan dishes act like cosmic megaphones, allowing us to communicate with spacecraft traveling beyond our planet. Now let's discuss its role in the Voyager missions. The Voyager probes, equipped with cameras, sensors, and instruments, served as our eyes and ears in the vastness of space. To make sense of the data they sent back and to give them new instructions, we needed a robust communication system, and that's where the DSN stepped in. Picture this: Voyager 1, on its way to the outer reaches of the solar system, sends a message back to Earth. It's a faint signal traveling at the speed of light. As it traverses the cosmic expanse, it weakens. By the time it reaches Earth, it's barely a whisper. But the DSN's colossal antennas are poised to catch that whisper. They lock onto Voyager's feeble signal and amplify it, turning it into data that scientists can analyze. The DSN doesn't just receive signals. It also sends commands. Voyager missions are dynamic, requiring scientists and engineers to tweak their plans, redirect the spacecraft, or adjust their instruments. They send these commands via the DSN, which beams them into space to reach Voyager. It's a two-way conversation between Earth and the farthest human-made objects in the cosmos. One remarkable aspect of the DSN is its 24/7 operation, tirelessly listening for those distant signals. It's like having an unblinking eye on the cosmos, keeping us connected with our spacecraft even when they're billions of miles away. The Voyager missions stand as a testament to the power of collaboration and innovation. While the spacecraft embarked on their incredible journeys, the DSN ensured they were never truly alone, bridging the gap between our planet and the unknown. It allowed us to explore the outer planets and venture into interstellar space. In essence, the Deep Space Network isn't just a collection of antennas. It's our lifeline to the cosmos. It ensures that the stories of the Voyager missions continue to be written even as the spacecraft journey beyond our solar system into the uncharted territory of interstellar space. So what is the heliopause, and what did Voyager 2 discover there? As the Voyager probes embarked on their interstellar journey, a crucial milestone awaited them: the heliopause. This boundary marks the separation between our sun's influence and the expansive interstellar space beyond. The exact location of the heliopause was a mystery, with initial estimates placing it near Jupiter. However, refined calculations by astronomer Bill Gurnett in 1993 narrowed it down to a range of 116 to 177 astronomical units. To put this in perspective, 1 astronomical unit is approximately 93 million miles. The distance from Earth to the Sun. Gurnett's projections proved remarkably accurate when Voyager 1 reached the heliopause about 2 decades later, detecting the expected rise in plasma density. However, an intriguing puzzle emerged. Despite observing an increase in plasma density, Voyager 1 did not register a significant shift in the ambient magnetic field direction. This was unexpected, as a transition from a region where the magnetic field originated from the Sun to one influenced by other stars should have been noticeable. The mystery deepened when Voyager 2 reached the heliopause at the same distance as its twin, 120 astronomical units from Earth, but also failed to detect magnetic field changes. Theoretical models predicting the behavior of the heliosphere and its interaction with the interstellar environment faced challenges due to these unexpected observations. The heliosphere was anticipated to fluctuate with the Sun's 11-year cycle, which did not align with the Voyager data. Despite these challenges, the Voyager data have provided valuable insights for refining theoretical models. Scientists now propose that our Sun has transitioned from a hot ionized zone to a partially ionized section of our galaxy, likely triggered by nearby supernovae. These ancient exploding stars heated the surrounding area while removing electrons from adjacent atoms, creating a boundary reminiscent of a turbulent side with mixed magnetic fields. The Voyager probes, Voyager 1 and Voyager 2, continue their ageless journeys through interstellar space, leaving behind the planets and moons they once called home. The cosmic future for these indefatigable travelers remains uncertain, but various possibilities abound, racing in different directions. With Voyager 1 heading toward the constellation Hercules and Voyager 2 making its way toward the constellation Cetus, they might outlast our species, enduring for millions of years. While some scientists predict a potential cosmic end in 2030, there's also the intriguing possibility that these probes could encounter other star systems, carrying with them a message from a long-lost Earth. Imagine an alien civilization stumbling upon these ancient artifacts of human ingenuity, including the Golden Record, a time capsule of our existence. The mysteries they might uncover are boundless.